All right, everybody, we're going to be working on simplifying some radical expressions. So we're going to be working with different operations, adding, subtracting, multiplying, and dividing. And these are going to have nth roots. So you're going to want to grab your calculator so that we can work with simplifying these radicals. So there are 6 examples. Let's go ahead and get started. Alright, so the first type we're going to work with are adding and subtracting. And the key is that the number under the radical, so the number under the radical, whatever type of radical it is called the radicand. Okay, and the radicands, in order to add them or subtract them, they must be the same. So basically you cannot add a square root of 3 plus a square root of 2. It would just remain just like that. That's as simple as that gets. So because the square root of 3 and the square root of 2 are different, radicands, we cannot add them. If it was the square root of 3 plus the square root of 3, well then we can say we have 2 square roots of 3. So that's the idea, is we first have to figure out what type of radical we've got and then simplify it and see if we can combine it with any other radical that's there. So example number 1 is the cube root of 250. So I'm going to have to start to break down 250, and I know that it is 2 times 125. And 125 is 5 times 5 times 5. So this is, as we broke it down in the last video, 5 cube root, and then there's a leftover 2. So let's work with the next one. 16 is 2 times 2 makes 4, 8, and 16. So this is also a perfect cube right there. Now this 2 is going to get multiplied by the 2 that's on the outside, so that's going to be plus 4 cube root of 2. So remember, we're multiplying the 2 that came from the perfect cube times the 2 that's already out there, and we still have a 2 that's left over. So now that I have the same radicand and the same type of radical, that's really important. You can't have a square root of 2 and a cube root of 2 and combine them. They have to be the same type of radical. So this results in 9 cube root of 2. Okay, so all of this has to be done on the calculator. It just maybe you want to have the calculator if you're working with breaking these down into prime factorization. All right, let's take a look at the next one. The next one is a square root here. So I'm going to have, let's see, that's 5 times 5 makes 25 times 3. So there's my perfect square. So this is 5 square root of 3. The next one is a perfect cube, and it's negative. That's important to keep in mind, because this is saying this is negative 4 times negative 4 times negative 4, which means that what goes on the outside is a negative 4, but there's already a negative out there. So this actually turns into plus a 4. There's no more cube root because we had a perfect cube. And lastly, 27 is made up of 3 times 3 times 3, but since it's only a square root that I'm looking for, that 3 gets multiplied by the outside 4 to give us 12, leaving behind a square root of 3. So once I've simplified them individually, then I can go ahead and add them together. And that leaves me with 17 square root of 3 plus 4. This could be written, and it would be absolutely correct if you wrote it as 4 plus 17 root 3. This doesn't matter. There's no right or wrong way of writing these, so long as you know you're not adding the 4 with the 17, because the 17 belongs to the radical. All right, let's move on to multiplication. All right, for multiplication, you actually get to multiply what's underneath of the radical so long as it's the same type of radical. So since these are both fourth roots, I can multiply m cubed times m to the 7th. This would be similar if I had the square root of 2 times the square root of 3, that I would actually get the square root of 6. Now in the event that you multiply something like the square root of 6 times the square root of 2, and you get the square root of 12, that this actually could be broken down to 2 times 2 times 3, you would have to continue to simplify it. So we'll go ahead and take a look here. So the fourth roots, so I'm going to get a fourth root of, and since when you're adding these together, or multiplying these together, excuse me, you actually add exponents, that's one of our properties, that this becomes m to the power of 10. Well, since I'm working with perfect 4s, then I know I've got 10 of them, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, that I'm going to have 2 perfect groups. Now if you can do this without actually writing them all out, that's totally fine, leaving me with m squared times the fourth root of m squared. Okay, let's move on to the next one. In this case, we're going to be using distribution. I'm going to set it up using the box, the Punnett rectangle, if you will, because I like the organization. Since I have 3 terms here, I'm going to make that across the top. So it's 13 squared. I'm not going to simplify 13 squared. I'm just going to leave it. And then the cube root of 13 and a minus 5. And then down the side I've got 2 and the cube root of 13. Now these problems are set up intentionally to reduce for us, and that's nice. So it's really just exercising our multiplication and our awareness of the different types of radicals. So when you multiply this one, I do get 2 times the cube root of 13 squared. And here I will have 2 times the cube root of 13. And then I have minus 10. And here I'm going to get the cube root, but I'm going to get 13 cubed because I have a squared and a single. And here I will have the cube root of 13 squared. And lastly, I've got minus 5 times the cube root of 13. So making sure you make your boxes big enough is probably a good idea. All right, so getting to combine these, I can see that I've got these 2 that are 13 squareds. So that makes that a 3 cube root of 13 squared. And if at this point you want to make that 169, totally fine. And then I see that I've got, let's see, these 2 right here can go together because that is going to be minus 3 times the cube root of 13. Those are different. I can't combine them. And then I've got this minus 10, and this one is a perfect cube. It's like the inverse operations are going to just make that 13. So if this is 13 minus the 10, then it's actually just a plus 3. And once again, these can be written in any order. I'm just going to leave it like that. All right, next up is division. So we're dividing radicals or radicals that involve division, and we're also going to be working with rationalizing. So if you can recall that rationalizing like 1 over the square root of 2, you'd have to multiply the numerator and the denominator by the same thing, giving you the square root of 2. The bottom, because you have a square root and now you have 2 2's, that it just becomes a 2. So it's not just that the radical cancels because you multiply it by itself, it's because you formed a perfect square. And this is where some confusion comes in. I'm going to just warn you that if I'm working with a fourth root, I can't just multiply it by 1 more. I have to complete a perfect fourth. So let's go through the steps for the first one. The first thing we're going to do is use this division property where I can actually split these up. And the reason that I want to do that is because a radical in the numerator is totally fine. It's a radical in the denominator that we're going to be working with. So I need to create 4 of these 5's in order to break it out of the radical. So I have to very carefully choose what I'm going to multiply it by. And it's going to be 5 to the 3rd power, because when I combine those together, I get 5 to the 4th. And a 4th root of 5 to the 4th, they cancel, and that's when I'm going to get the 5. So that's the same idea here, but with the square roots, we only needed to multiply by itself because that's how you square things. So I will multiply the same thing in the numerator, and that's the 5 cubed. So my denominator does become 5 because combining these gives me the 4th root of 5 to the 4th. In the numerator, I have 3 times 5 times 5 times 5 under my 4th root. None of those are perfect 4's, but I can combine them, and I should get 375. So I would have the 4th root of 375 that cannot actually be broken down anymore. All right, let's look through the next one. There's a few options for this. I'm going to go about it in one way, and we can talk about a different approach to this when we're together. So remind me that I want to go through a different route for this. But the first way is going to be exactly the same thing we did here. I am going to complete perfect fourths. Since this is x cubed, I only need 1 more to make a perfect fourth. But since this is y squared, I'm going to need 2 more. And whatever I do to the denominator, I do to the numerator. So you have to decide that I needed this to make x to the 4th, and I needed a y squared to make y to the fourth, because when you take the fourth root of x to the fourth, y to the fourth, you're just going to get xy. So you won't get what's under the radical. You will get the completed fourths. Okay. Now the numerator is now going to become the fourth root, and I'm going to have x squared, and I will have y to the fifth power. So bringing this down, I can see that there's actually a perfect fourth that was created in my numerator. So I'm working with the numerator right now. And the numerator has x, x, and then y, 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 y. So there's my perfect fourth. So I will take that out. I still have the fourth root of x squared and a y, and my denominator is xy. Last step would be to reduce on the outside. And that leaves the fourth root of x squared y over just an x, because my y's would be able to cancel now that they're both outside of the radical. Okay, remind me again, I can show you a different way to approach this type of problem, and you may like the other way, or you may find this one to be working just fine. So great job, and we'll continue when we're together.